Okay, welcome to another short lecture of OpenStack's astronomy. Here we'll be talking about Chapter 8, and we're going to put our geology hat on. And before we explore other planets within our solar system, we have to first get a good understanding of our own planet, see how it actually works, and from there we can make inferences to other planets. So in this chapter, we'll look at the Earth here. And so kind of looking at our global perspective here. And what do we know? What is our understanding of geological features from observations here and experiments that we've done here on Earth? So again, this is going to be a quick overview. You could take a full course in geology, understanding the interior of the Earth and how it works. So this is a very simplified model and a very simplified explanation of some of the key features. So Earth's interior consists mainly of a core, mantle, and crust. So the core, which is going to be more dense, so more density, the more things will contract and go towards the center of an object. So you're going to have nickel and iron, kind of a molten liquid in the core. Then we have the mantle, which is going to be minerals, oxygen, etc. And then the crust on the outer layer, which is low density, kind of granite. On the outer layer, also you have the lithosphere, which contains the crust and the mantle as well. But again, this is a very simplified model of what we know of the interior of the Earth. So how does this compare to the other terrestrial planets? And we could see that the core of the Earth is very similar to that of Venus. They're similar in size, and so these resemble one another. Mars is a bit smaller, but those proportions are still there, as is the moon as well. The moon is not a planet, but we typically bundle it up when we talk about the terrestrial planets because it's made up of the same compositions. And Mercury is kind of the oddball here with its large core. You could see a lot larger than the cores of the other terrestrial planets. And we'll talk more about that as well. So what drives heat activity or geological activity here? And it has to do with convection. So hot rocks rise and then cool rocks fall. And we have this cycle that goes on within the Earth. So things that are hotter always rise, and then cooling rocks come down. And this takes a very, very long process. We're talking hundreds of millions of years here for this to actually cycle through. And so this mantle convection here creates that heat that drives geological activity. Also, the Earth has a magnetic field. So if we have a heat source and we have a rotation, then that will create a magnetic field, much kind of like a generator. So whenever we observe any object, if it has that magnetic field, we could infer that there's a heat source, some geological activity, and through observations, we see that it will be rotating. And so the magnetic field protects us from the solar winds. Although the sun gives us life, it is also radioactive, and our magnetic field helps us with that. This creates ionized or charged particles that tend to flow along it, and they will enter on the north and south poles, creating what are called the aurora borealis, these huge spectacular light shows close to the poles. So, looking at Earth's crust, how does the surface of the Earth change? Now that we know that there's a heat source and there's geological activity happening, then that means the surface is able to change. And four ways: impact cratering, volcanoes, tectonics, plate tectonics, and erosions. Those are the four main ways that the surface of our Earth changes. So here we see some impact craters. This is Meteor Crater in Arizona, about a 50,000-year-old impact, and we could still see the shape of it, the large impact there. Erosion has occurred here, but it's very large, where the crater itself still remains there. And we think something perhaps about 40 meters that was iron perhaps hit the Arizona desert here. Some even larger here in the Gulf of Mexico, the Yucatan Peninsula. We think is the crash site of a crater or of a meteor that actually impacted 65 million years ago that extincted the dinosaurs. So another way that the surface changes is with volcanoes. So molten rock, right, magma, finds its way up to the surface and flows out. And as the lava carves out, it kind of resurfaces, so paves the surface again. Places like Hawaii or so, it actually creates those islands. So volcanoes are able to contribute to changing the landscape. They also emit a lot of outgassing, and we'll talk a little bit more about the cycle associated with this. But again, getting a lot of the interior of the Earth and then releasing that out into the atmosphere. Tectonics. This is the third way that the surface changes. So huge plates could either merge together or pull apart to create mountain ranges or valleys. So the Himalaya mountains are a result of two major plates pressing together. Here's an image of the continental plates here. So we could see here in North America, we have our Pacific plate. And the edge of the plate is, we're probably more familiar with the San Andreas Fault there. So that's why we're prone to earthquakes where we live, because these plates tend to shift and it will shake the ground. And fourth is erosion. So water from the Colorado River has carved out the Grand Canyon. So this small river just chopping away for millions of years created this large canyon. If you've ever been up to Yosemite, the valley, ice glaciers, when they melt, have carved that out, again, over a long period of time. Dunes, sand dunes, wind kind of tears away at rocks. So very, very slowly creating that fine dust. And then erosion. So looking kind of here at deltas where waterways meet and just bringing that settlement and just eroding away there. So those are the four main ways that we see the surface change for us on Earth. And, you know, an example of something like this is if you've ever been out to the beach, you dig a hole, and if you stand back, you kind of see the water that starts covering it, right, little by little. And so around the edges, they become more smoother, and eventually the hole just fills up like nothing was ever there. So if we see evidence of undisturbed craters or holes or surfaces there, then we know there's not much geological activity happening there. So looking at Mercury and the moon, we don't really see that much. We see craters that kind of have been there, and craters with other crater impacts there. So we could see that there's not geological activity happening. That's what we would call the planets are geologically dead or inactive. Venus, we see that there's large volcanoes, so the lava tends to cover its surface. We know that's going to be active. And then Mars, there is some activity there, huge sandstorms that happen. But we see evidence of a kind of erosion in these canals of water flow that perhaps in the past gives us evidence that there was large oceans or large bodies of water there. Our Earth, the atmosphere again protects us. It blocks out some of the electromagnetic spectrum that is a bit dangerous to us. But how does it actually affect us? Well, apart from protecting us from the radiation, it also does a greenhouse effect. So similar to how Venus, right? Venus has a runaway greenhouse effect where the temperatures are 900 degrees all of the time. Here we have a thinner atmosphere, so it's kind of like a blanket that gets put on us, but not as thick. So it actually helps to stabilize our climate. So the temperature is roughly about the same throughout the Earth there. And of course, it adds to making our skies blue as it just reflects blue light or scatters blue light a bit easier. Here on Earth, we have weather, right, and climate. So this really helps out to stabilize things. This is part of the, due to the geological activity that we have there. So weather, climate, we know that bodies are active. And this has to do, again, with the slight tilt of the axis rotation. How does weather change long term? Well, because of that axis tilt, again, we have gone through cycles where it gets extremely cold and then it warms up. So this idea of extreme temperature changing, with global warming, it is true that it is a natural phenomena where we go through these cycles here. But again, the concern is at the rate at which it's changing. It ends up being an issue. But we see these CO2s from outgassing, right, will build up into oceans and they're frozen, and then ultimately they get released. So there is this natural cycle of those gases, but it takes a long time for that. With us digging up fossil fuels, the argument is that we're speeding up that process a lot faster. So we've heard of our water cycle, right? So water evaporates, goes up into clouds, falls down, goes into our ocean, and cycles again. Well, here we have our carbon dioxide cycle. And so similar to that, where it's in the atmosphere, the CO2 dissolves in rainwater. The rain erodes, right? These minerals end up flowing. And then it goes into the rocks, into our ocean. And then eventually it's carried down into the mantle. And then the rocks melt right in the mantle, and these outgases come back out as CO2 into the atmosphere. So this is a very healthy cycle. We want these greenhouse gases in our atmosphere, but at a steady level. We don't want to have them come out faster than they should. And by us extracting things in the ground, it adds to having this cycle speed itself up. But this carbon dioxide cycle is helpful, again, for stability within the Earth. And so here we have just an image of temperature and our CO2 emissions. And we could see that there's a relationship there. Whenever we get a peak here, we would also get a peak in the other graph there. And so when there is a low point here, then we also have a low point. So we see that there's a relationship between the CO2 when that increases and then the temperature. And so the concern is that really these last, few, perhaps over the last, century or so, a little over the last century, mainly really from the Industrial Revolution, we see that those levels have now started to just increase exponentially. And so that's a concern with our global warming, that we're extracting these fossils, or that a bit faster than they should. And again, the concern is that this is what we feel happened in Venus, where it does have that runaway greenhouse effect, and now the temperatures are unsustainable, 900 degrees all the time, all over the planet. So these are some key features, characteristics that we'll take away from Earth, and we'll keep these in mind as we start exploring some of the other planets and moons within our solar system.